All right, hello everybody. My name is Leland Tien. I'm a first-year master's student in the Department of Mechanical Engineering with a fluid mechanics focus, and this is my ME 513 final project. I decided to take a look at the classic fundamental problem in convection, convection of a flat plate under laminar flow conditions, and analytically compare some common methods of analysis. So let's dive into it. The three methods I decided to use were COMSOL, integral solutions, and similarity solutions. And I decided to look at 9 different fluids. Those 9 fluids are listed over here in the table on the right, starting with mercury, a very low Prandtl number, and finishing off with a very high Prandtl number of glycerol. You may be asking, what are these custom fluids 1, 2, and 3? Well, COMSOL's library of materials didn't have any fluids that had Prandtl numbers in this range here, so I made custom materials and adjusted their viscosity and thermal conductivity to match the Prandtl numbers found in the table there. So for those 9 different fluids, I ran the calculations and simulations underneath 2 experimental conditions. One with the isothermal plate, which is of course a fixed temperature for the entirety of the plate, and 2, a plate with constant heat flux, and that, to remind you, is when there is a constant rate of heat transfer from the plate to the fluid amongst the entirety of the plate. So let's take a look at a little bit of the motivation and background for doing this. Why study convection at all? It's important in microelectronics, HVAC, cooking, vehicles, weather. I could go on and on and on. And given that convection is an important thing to study in science, there's many different ways to approach convection problems, so I wanted to get a bit better understanding of the pros and cons for each method. So what are these methods? How am I going to compare them? Well, like I had already mentioned, 3 methods I'm going to use are the similarity solution, integral solution, and COMSOL. And because I couldn't find experimental results to compare these methods against, I'm going to treat COMSOL as the most accurate method and compare the similarity solution and integral solution against them. So let me just take you through the workflow process here of my project. We start with a given method. That method is going to deliver a result. So for the similarity solution, it's going to end up with a Nusselt function with the shooting method for the isothermal plate and just a direct general correlation for the Nusselt function for the constant heat flux condition. Integral solution, of course, arrives at a Nusselt function. And for COMSOL, that couldn't output a Nusselt function, so I had it, depending on the case it was looking at, for the constant heat flux condition, I had it output the plate temperature. For the isothermal plate, I had it output the heat flux. So taking all of the results, I refined them to find the local heat transfer coefficient H, and then I computed the integral of H over the length of the plate from 0.2 to 4 meters to gather a scoring, or make a scoring for the particular method that I'm looking at, so I can evaluate the profile as a whole, not as just one point. And you may be asking why from 0.2 to 4 meters and not 0 to 4 meters. Well, there's some irregularities in the range from 0 to 0.2, especially for the COMSOL calculations. So once I've got this scoring by integrating H, I find the percent difference of those scores versus the COMSOL value. And so naturally the question is, why is COMSOL more accurate? I thought I'd address a few of the reasons. Of course, for the Navier-Stokes equations, there are no analytical solutions in general, so numerical solutions are the best option we have for solutions. Also, COMSOL doesn't have to make slenderness postulate idealizations, so that makes COMSOL valid for very low Reynolds number flows. And the slenderness postulate idealizations are something that have to be made to carry out the similarity solutions and integral solutions. And I think perhaps the most important advantage that COMSOL has over the other 2 methods is that the fluid properties are not locked to film temperature. Being a finite elements program, it can treat every individual element with its own set of fluid properties. And for the similarity and integral solutions, I had to treat the whole system with a blanket set of constant fluid properties. So let me show you a little bit more about the COMSOL simulation. So for the constant heat flux condition, I held the free stream temperature to 300 K and the heat flux density to 100 watts per meter squared. And just a reminder, when we go to calculate the local heat transfer coefficient, This is the equation. So for the constant heat flux condition, we know Q double prime, we know T infinity, so I have COMSOL calculate T naught, the plate temperature for the constant heat flux condition, so I can finally close the problem, or close this equation, and calculate H. Likewise for the isothermal plate, free stream temperature is 280 Kelvin, plate temperature is 320 Kelvin, so we know delta T on the bottom. I'll have COMSOL calculate the local heat flux Q double prime, then H is closed. We can solve for H. So just to go over the simulation that I set up here, here's the graphics of it. This is largely identical to the simulation that Dr. Ramos showed us earlier on this semester in COMSOL. So just to remind you, on the leftmost side here I have the gas inlet, and for this first chamber here, the bottom has a boundary condition of symmetry, and the top of both chambers have an open boundary such that they're not chambers at all, and so it doesn't model confined flow. This is a free flow. And then at the boundary to the plate, we have a fixed temperature. The bottom of the boundary here for the plate, of course, is a wall with no permeability, and depending on the simulation I ran, I either had a fixed temperature boundary condition or a fixed heat flux condition. And over at the rightmost side, there's an outlet with a zero pressure boundary condition. So let's take a look at some of the results from COMSOL. I'm going to use water as a representative case and carry you through some of the calculations I did for water, and that's representative of what I did for all of the fluids. So for the isothermal plate, like I said, heat flux is the desired output from COMSOL, and this is the little bit of irregularity that I'm talking about at the beginning of the plate. So, and this is also the data that I exported into MATLAB to finally calculate the local heat transfer coefficient. And likewise for heat flux, I outputted local plate temperature as a function of the plate's length. And this is what I exported into MATLAB to finally calculate H, which I'll show you here. So here are the plots generated by MATLAB for the isothermal plate for water, given all three methods. So you can see that the integral and similarity solutions overestimated the local heat transfer coefficient relative to what COMSOL predicted. And again, just to remind you, the integral that I used to score these curves starts at about 0.2 here and takes this area to the end of the domain under the curve. And then for constant heat flux, you can see here a bit better separation in all three curves, but the opposite happens here. Integral and similarity solutions underestimate what COMSOL predicted for the local heat transfer coefficient. So once I calculated all these H values in MATLAB, I was able to also calculate those integrals from 0.2 to 4 meters, and I tabulated them for every particular experimental setup and every fluid in this table here. So just to give an example, percent difference for the integral method would be the integral of H for the integral method minus the integral of H for the COMSOL method, that quantity divided by the integral of H for the COMSOL method, and then I would take the absolute value of that. So I looked at the percent difference for all the different fluids and then calculated an average error to score the method as a whole. And contrary to what I was expecting, I thought that the similarity solution would produce the most accurate results. The similarity solution produced about twice the percent difference that the integral solution did. So for the isothermal plate, the integral method was the better method. And then the reverse happened for the constant heat flux condition. This acted as predicted. The similarity solution produced far more accurate results than the integral solution did, by again about a factor of 2. I also wanted to see if there was a correlation between the Prandtl number and the percent error from any given method, and I couldn't find any trend at all. So that told me that the percent error was not very sensitive to the Prandtl number. So moving on to conclusions. Objective, again, to remind you, analytically compare integral and similarity solutions against COMSOL. And the main takeaways for my research was that integral solution was more accurate for the isothermal condition, and the similarity solution was more accurate for the constant heat flux condition. Also of note, there was no clear trend between accuracy and Prandtl number. And I thought that this begs the question, why not always use COMSOL? So I thought I would list a few cons of COMSOL. First being that it's extremely expensive. Second, there's also a steep learning curve for the software. I've often heard regarding finite element packages that they can make a good engineer better and a bad engineer dangerous. So if you feed it garbage, it's going to output garbage. But if you know what you're doing, know how to set up the simulation well, you can output very meaningful results. And then I thought I'd build a table here just to kind of give a qualitative rating of all the different methods. COMSOL, intellectual effort was medium level, accuracy was very high, but then the cost, as I said, was very high. Integral and similarity solutions scored pretty much the same across the board, pretty high intellectual effort, as you'll remember from homework 3. Accuracy, based on my findings, were moderate. They weren't great, but they weren't bad. Cost is very low. You can do this with a pen, paper, and a calculator. So, with that said, if you're ever presented with a question on your comprehensive exams, what method is best, I have given you the answer so you don't look like this guy. Thank you for tuning in. I hope you enjoyed my presentation.